All right, so how do we treat Ka values with diprotic and polyprotic acids? Okay, important points. When an acid has more than one ionizable proton, the protons are lost in successive reactions, right? So this is how we look at the H's coming off. So if I'm looking at phosphoric acid, there's a Ka value for the first H coming off, a Ka value for the second H coming off, and a Ka value for the third H coming off. All right, so phosphoric acid is a weak acid, and it would have a small Ka value. But every Ka value after that would be even smaller. All right, so when you have multiple Ka values, the first H coming off is the easiest. What happens is electrons get back infused back into the structure and make it harder to take H's off. So the first H coming off is the easiest one, right? It's still a weak acid, right? 10 to the negative 3 in terms of a Ka value. But taking the next H off even, worse. I mean, ridiculously worse, right? So it's 10 to the negative 8 now. And if you're looking at the third H off, it's 10 to the negative 13. So you get to be a worse and worse acid as you take subsequent H's off. So most of the H, when you put phosphoric acid into solution, is because of the first H. All right, the contributions of dihydrogen phosphate and hydrogen phosphate are minimal. For weak polyprotic acid, the first ionization produces much of the H plus ions. All right, sulfuric acid is a weird acid. It's one of our seven strong ones, and it's the only diprotic or polyprotic acid that's a strong acid. And it's strong because of the first H, not the second one. So when we put sulfuric acid into water, the visualization is the first H completely coming off. So really that reverse arrow is non-existent. I mean, you put sulfuric acid in water, the H is off of um, the sulfuric acid to make hydrogen sulfate. Now the Ka value for hydrogen sulfate is small, right? It's less than 1, so this is a weak acid, but as far as weak acids go, it's pretty good. Nonetheless, though, almost all of your H comes off because of the first H. Or I should say, most of the H that's in the solution is because of the first H, not the second H. All right, calculate the pH of a zero point 0.5 molar sulfuric acid solution. All right, so if I'm starting out with 0.56 molar sulfuric acid, ready, set, go. It's all the sulfuric acid's gone, and it's turned into hydrogen sulfate and H plus ion. All right, so for the second ionizable proton with hydrogen sulfate, you're already starting out with a bunch of H plus ion already in there. So that's going to impede that next H coming off, right? It's going to shift the equilibrium back the other way. So when you start talking about taking the next H off of hydrogen sulfate, you've got high H plus concentration stopping that from happening. So you're going to get very little bit coming off. All right, so let's call that X. All right, so you're going to lose X amount of hydrogen sulfate. You're going to make X amount of sulfate and add X amount to your 0.56 molar H plus that's already floating around from the first ionization. So these are my equilibrium concentrations. Plug them into the Ka expression for hydrogen sulfate. Let's assume that I can ignore the change in concentration to the 0.56 molar hydrogen sulfate concentration. So basically, X is equal to 0.103. So how does that compare to my original concentration of 0.56 molar? It's only a 2.3% error, so this is legal. So in essence, what you're saying here is all the H is coming from the first ionization, not the second ionization. So take the negative log of 0.56 and you get a pH of 0.25. All right, salts that have acid-base properties. Um, A salt, by definition, is an ionic compound produced during an acid-base reaction, right? So when you react hydrochloric acid with sodium hydroxide, the salt is sodium chloride. But the salts could also be sodium nitrate or potassium sulfate, right? These are all salts. Sometimes the salts react with water, right? So if I have a cation or an anion that's going to react with the water to produce an acidic solution, we call this hydrolysis. All right, so the question is, what kind of a salt is going to affect the pH? All right, so salts that don't affect the pH. These are going to be salts that were made from strong acids and strong bases. So if I react sodium hydroxide or magnesium hydroxide with one of the 7 strong acids, I get a cation that's not going to interact with the water. I get a conjugate base from the strong acid that isn't going to interact with the water. Chloride ion is such a poor conjugate base. It's a non-base. Same with nitrate, same with perchlorate. So put these in water and they have no effect on the pH. Salts that produce basic solutions. All right, so if we have a strong acid having a conjugate base with no hydrolytic value, right, it's not going to react with the water. The salt of a weak acid does. All right, so the weaker the acid, the stronger its conjugate base. So if I have the salt that's made from reacting sodium hydroxide with acetic acid, right, I get sodium acetate. Acetate's a base. Acetate will react with water to produce hydroxide. Same with fluoride ion, right? Fluoride ion is the conjugate base of hydrofluoric acid. Cyanide ion is the conjugate base of hydrocyanic acid. So these significant bases will react with the water. The 1A and cation and the 2A cation don't react with the water. So if I put formate into water, it's going to have a Kb value, right? This is a Kb expression. So water is going to protonate formate to form formic acid and hydroxide. So what we're interested in is the hydroxide concentration, right? The hydroxide concentration is the thing in there that's affecting the pH. So the Kb value for formate is 5.6 times 10 to the minus 10. So it's a really weak base, but it's a base. So calculate the pH when you've got 0.4 molar solution of sodium formate. Again, we can discount the sodium ion. It's a spectator. It's about the formate. The formate getting protonated by water to produce hydroxide. So if I'm starting out with 0.24 molar sodium formate, I'm going to lose a very small amount of it, X. I'm going to make X amount of formic acid and X amount of hydroxide. If I solve for X, X will give me the hydroxide concentration. So again, I can ignore the change to the initial concentration because the Kb value is so small. Makes it easy to solve for, and once I got X, I got the hydroxide concentration. Take the negative log and get the pOH. Subtract from 14 and get the pH. So this is a problem, right? I mean, you'd have to be able to do this. Put sodium formate in water and figure out the pH of the solution. Percent hydrolysis is just the same as percent ionization, right? So we take the value of X and divide it by the initial concentration, multiply by 100 to get the percent hydrolysis in this case. All right, salts that produce acidic solutions. In this course, the only weak base we know is ammonia. So if I protonate ammonia, I make ammonium ion. Ammonium ion is a significant conjugate acid of that weak base. Chloride ion is the conjugate of hydrochloric acid, so it has no hydrolytic value. So a weak base with a strong acid makes a salt that'll change the pH when you put it into water. So if I put ammonium chloride into water, what I'd want to know is what the ammonium concentration is. All right, so if I've got 0.1 molar ammonium chloride, that's 0.1 molar ammonium ion. I'll lose X amount of that to produce X amount of ammonia, X amount of H plus ion. So again, it's a small amount, right? The Ka value for this was 10 to the negative 10. So X is really small. I can ignore the change in the initial concentration of the ammonium ion. So I can multiply both sides by 0.1, take the square root of both sides, solve for X. X is the H plus concentration. Take the negative log and get the pH. Salts of highly charged metal ions give acidic solutions. So how does this work? Well, when you take electrons away from metal, as we know, you've made something that's hungry for electrons. So if the aluminum ion, right, aluminum with a +3 charge, you've had to take 1, 2, 3 electrons off of it, gets in contact with water, it complexes with the water. So what does it mean to complex? It means that the water is donating electron pairs to covalently bond with the aluminum. And you've got 6 waters attached to this aluminum +3 ion, and you make this big polyatomic covalently bonded complex that has a +3 charge. Well, this thing in turn, because the aluminum ion pulls so hard on electrons, weakens one of the bonds in the waters, and the H pops off. So by pulling electrons away from the OH bond, you end up producing an acidic environment. Now, this isn't a strong acid. Nonetheless, it does make the solution acidic. So let's pick aluminum 3+, right? This is something we've had to take 3 electrons off of, so it's hungry for electrons. So when it gets in contact with the 6 waters, it's trying to pull the electron, those lone pairs, off of that water, and you get covalent bonding between the aluminum 3+ and the waters. Now, this whole thing has a +3 charge. By pulling so hard on the electrons, it weakens one of these, the water's OH bonds, and the electrons get transferred to the complex to try to stabilize it, and the H plus ion slips off. So iron 2+, zinc 2+, nickel 2+, iron 3+, chromium 3+, and aluminum 3+, all have Ka values. So they pull hard enough on electrons attached to that they attach to when they form complexes to give an acidic solution. Now, these are small Ka values, but nonetheless, the solution gets acidic. Greater the charge, the more acidic the cation. All right, salts in which both the cation and the anion hydrolyze. So general rules. The Kb value for the anion is greater than the Ka value for the cation. Then the solution is going to be basic, right? So the anion of a weak acid would have a Kb value better than the conjugate acid of a weak base. So for example, when you put ammonium cyanide in water, ammonium ion has a Ka value of 5.5 times 10 to the negative 10, whereas the cyanide ion, right, the conjugate base of hydrocyanic acid, has a Kb value of 10 to the negative 5, right? So this is a much bigger Kb value than the Ka value for ammonium ion. So that's what's going to affect the solution, the cyanide ion. There are all alternative situations where the Kb value for the anion is less than the Ka value for the cation. Then the solution would be acidic. And when the Ka value and the Kb value for the cation and the anion are close, then you have close to a neutral solution. So that's how it works.